Hello, everyone. This is the video lecture of section 5.9, part 2, second part of 2 parts. Okay, so in the first part of this section, we learned about approximation, 2 different approximation methods for definite integral. One is midpoint rule, and the other is trapezoidal rule. Today we are going to in this second part, we're going to study the Simpson's rule. So, in Simpson's rule, what we're doing is this. Let's say you have something like this, and then you have, let's say, you have 6 subintervals, n equals 6 case. Then the idea of Simpson's rule is this. We're using also uniform partition, which means from A to B, delta x is equal to b minus a over n. N equals 6 in this case, but what we're going to do is that we try to find the quadratic function going through those 3 points, like quadratic function. Some quadratic function going, so we combine every 2 intervals and they try to find quadratic function going through those 3 points and then use the area under that parabola. Alright? That would be a little bit of. Okay? So we have to know how to get the quadratic function when you're given 3 points. Quadratic function has 3 parameters, ax squared plus bx plus c. So in order to have unique one parabola going through 3 points, you need to have 3 equations, 3 conditions to determine those parameter values. So when you have a 3 points, you can get second degree equations going through those 3 points. So now, let's think about the very simple case. So let's say 0 minus h and h. Say you have something like this. These, let's say, you have these 3 points. How do we find, let's say, this is minus hz0, and this is 0, z1, and hz2. So z0, z1, and z2 are the y coordinate values of these 3 points. And they are, the interval size is h, right? So given these 3 points, hz2, find quadratic function up to degree 2, which passes through them all. Okay? So we have to determine A, B, C values so that this graph will go through these three points. Okay? Now, by plugging in this, the first condition, when h equals negative h, y equals z0. So you'll have z0 y equals minus h squared is just h squared, right? H squared a h squared minus h minus bh plus c. From here, x equals 0, y equals z1. X equals 0, all 0, only c. z2 equals when x equals h. So h squared plus bh plus c. Now, if we do at z0 or z1 plus z2, then adding these 2 and then 4 times, so you 4 and 4, if you add them up, 2ah squared, these one cancel, 6c. So remember this, okay? Now, then what is the area under this problem, or integration of this function? Ax squared plus bx plus c, which going through these 3 points. So let's consider this integral minus h to h, ax squared, bx plus c dx. First of all, this is arc function. Arc function's integral from minus h to h, symmetry interval will be 0. So it'll be just only this one, right? Arc function means you have, origin symmetry. In the case, up here, down here, cancel. So definitely will be 0. So, and then this one is even function, so it is just 2 times 0 to h, right? When you have an even function, so symmetry with respect to, minus h to h, when you have a y symmetry like even function, then definite integral from minus h to h is just this integral twice. Okay? And that is what? So I'm going to write it. dx. And that is 2 times a over 3 x cubed 0 to h cx 0 to h. So this is 2/3 of ah cubed plus 2ch, right? Now factor h over 3. Factor h over 3. Then h squared is remaining 2a. 2ah squared is remaining. H 1/3 out, then 6c. Now look at the start. This is h over 3 and z0 plus 4z1 plus z2. So what is it? The definite integral of second degree quadratic function through these 3 points, minus h z0, z0, z1, h z2, that will be just h over 3 times this y value plus 4 times this y value, center y value, and then plus the third y value. Okay? Now, this is from minus h0h. Even if you have, let's say, somewhere else, let's say, some a plus h, a plus 2h. Let's say you have same situation. A z0, a plus h z1, and a plus 2h z2. Even if it happens over here, so if these y values are 0 and the interval size is h, no matter where it is, so you can just move this one all the way to 0 and negative h and h, right? Yeah, then the equation itself, the function, quadratic function itself will be changing. But this area must be same as this area, right? So, in the end, no matter where you are located, the definite integral of a quadratic functions between a to a plus 2h with y value z0, z1, z2 will be always this. Okay? You get that? If you use translation, you can match. Alright? So this one case is good enough. So then, as we saw before, if you have these kind of cases, let's say, what happens? So we want to have pair, two subintervals pair. Each one we are going to use quadratic function through those 3 points. All right, and use those functions, quadratic function, as a approximate tool. So you can take a look at example, figure 7 on page 406. Okay. So in this case, this is x0, x1, x2, x3, x4, x5, let's say x6, let's say it keeps going. And here h, this is h, right? This is h. H equals delta x, which is b minus a over n. Okay? And I'm going to call you yi as a function value of. So instead of zi, I have yi. Why did I use z? I could have used yi. Then this area is a1. Let's say a2, a3. So in order for this to work, we have to have even number only. Even number. Okay? So we only consider even number. N equals 2 times n. So if n equals 10, n equals 5. Alright? Then a1, a2, a3, all the way to am, right? This two parts together a1, next two parts together a2, and so on. So am will cover 2m parts, so n, the entire one. Okay? So this is according to this formula, h over 3, y0, 4y1, y2. Okay? Next one, h over 3. Now, this is new z0, z1, z2. So that will be y2, 4y3, y4, right? For A3, this is your z1 value, z0, z1, z2 value, right? So this time y4 is the beginning, 4, y5, y6, all the way to. You will have a last three, y2n minus 2, 4, y2n minus 1, plus yn. You add them up. Then the area, we call it Sm. S for Simpson's rule. Simpson's rule. H over 3. Now, all the odd terms will have 4 times. And then the even terms will have twice. Except for the very first and the very last. y0, 2y2, 4y1, 2y2, 4y3, 2y4, all the way to 2yn minus 2, not 2n, n minus 2, n minus 1, 4yn minus 1 plus yn. Okay? That will be the result. This is what we call Simpson's rule. Okay? So, let's summarize what we just found. Simpson's rule. That is, only when n is even. Okay? Then your definite integral can be approximated by Simpson's rule. Instead of h, okay, delta x over 3. Alright? y0, 4y1, 2y2, 4y3, 2y4, all the way. 2yn minus 2, 4, yn minus 1, yn. Okay? So every odd terms will have a multiplied by 4, every even terms will be multiplied by 2, except the very first and very end. Okay? That's the Simpson's rule. And ESN will be the error due to Simpson's rule. Okay? Now, then there is also another theorem for error bound, maximum possible error bound for Simpson's rule. That is error bound for Simpson's rule. That is, now this time, the error bound theorem for trapezoidal rule and the midpoint rule had a second order derivative less than or equal to k, right? And here we need fourth order derivative. If fourth order derivative of x is always less than or equal to capital K on that interval, then absolute value of the error due to Simpson's rule is always less than or equal to k times b minus a to the fifth power over 180 times n to the fourth. Now this is the key. K, b minus a, 180, these are all fixed numbers. The only thing you can choose is n number, right? Look at this. N to the fourth. So worst case possible error, maximum error, error of upper bound of the error is proportional, inverse proportional to n to the 4. So if n increases by 2, the error, upper bound of error will decrease by 16, 1 over 60. Okay? This is way faster than trapezoidal rule or midpoint rule. Okay? Now, let's do some examples. Example 2a, approximate integral from 0 to 1 to 2, just like before, 1 to 2, 1 over x dx, using S4. B, find an error bound for S4 and that means this value and actual error size. Okay? So A. So S4 means that what is it? Your delta x equals 1 over 4. X is 0 equals 1. X1 equals 5 over 4. X2 equals 6 over 4, 3 over 2. X3 equals 7 over 4. X4 equals 2. Right? 1/4 each time. Now, then corresponding y value will be reciprocal. Y1 equals 4 over 5 because your function is 1 over x. Y2 will be 2 over 3. Y3 equals 4 over 7. Y4 equals 1/2. Y4. So, your S4 is delta x over 3. 1/3 of delta x. Y0, which is 1. 4 times Y1. 4 over 5. 2 times Y2, right? 2 over 3. And then another 4 times this one, odd term. And then final one, as it is. And if you do that, you're going to get about 0.693254. Okay? Now, what about error bounds? This one. We're talking about this one, error bound. In order to find k, we have to take the derivative. F of x equals x to the negative 1. F prime, negative 1, x to the negative 2. F double prime, 2x to the negative 3. Third order derivative, minus 6x to the negative 4. Fourth order derivative, 24x to the negative 5. Okay? And then, fourth order derivative of x, absolute value, 24 over x to the 5th. Okay, think about it. X is between 1 and 2. This is the largest when x equals 1, right? When x equals 1. 24, okay? On this interval, right? This is the largest possibility, which is when x equals 1. So, k equals 24. Therefore, this k, b minus a to the 5th over 180, and to the 4th, all the values plug in, 24 times 1 to the 5th, 2 minus 1 is 1, 108 times n equals 4, 4 to the 4th, which is about 0.0005283. This is upper bound of the error, worst possible case. All right? What is actual error? One to 2, 1 over x dx minus S4. This is ln of 2, actual value ln of 2, minus 0.69, 3 to 5, 54, which is around 0.000107. Now, compare that with the previous value. Even when we use slightly larger than n equals 5, when we use n equals 5, the error due to even midpoint rule was 0.001239. So this is less than 10%, right? 1/10. So it's much better, right? With even smaller n value, because we have n to the 4th dependence, okay, in the denominator. Okay, now last one is, I'm gonna need this. Okay, I'm gonna just write it later. Example 3. How large n should you take? How large n should you take in order to guarantee that the approximation of this integral is accurate to within 0.0001 for 3 different approximation methods: trapezoidal rule, midpoint rule, and Simpson's rule. Obviously, we have to consider the worst possible case error being less than or equal to this, right? The worst possible case error was given by theorem 1 and 2, right? So, solution. First of all, we find the k value for theorem 1. In that case, that was 2 over x cubed. So absolute value of second order derivative then equals 2 on 1, 2. This is our k value, right? And then largest possible error from the theorem 1, okay? That was k times b minus a to the 3rd power over 12 n squared. In this case, 2 and 1, right? Over 12 n squared. So 1 over 6 n squared. Okay? Now we want, this is a maximum possible error. In order to guarantee that our error is less than or equal to this, then our maximum possible error must be less than or equal to this. We're trying to be conservative here. Which means n squared, multiply both sides by n squared, greater than 1 over 6 times 0.0001. Okay? Which is about n squared. And then you have to take square root. That means x must be greater than or equal to 8. So, 40 is not enough, 41 should be enough. So to be absolutely sure, we have to choose 41, next one. Okay? That's A. Now B, same thing, we use the same K value. Midpoint whose error bound was same thing except for this one to be replaced with 24, right? So 2 over 24 n squared, so 1 over 12 n squared. We want this maximum possible error to be less than this one. Therefore, n squared must be greater than 1 over 12 times 0.0001. If you take square roots, this must be greater than 28.87. So if you want to use midpoint rule, you have to divide your interval up to 29 interval. If you want to make sure that your error is absolutely smaller than this. Okay? Quite a lot. What about Simpson's rule? For Simpson's rule, we already found that this thing, 24 over x to the fifth, is less than or equal to 24. This is our K value. Alright? And the absolute value of error from Simpson's rule is, remember, less than or equal to b minus a to the fifth over 180 n to the fourth. Plug it in. 24 times 1 to the fifth, 180 n to the fourth. Now we want this to be less than 0.001. Even the worst possible, largest possible error, still less than this. This will be n to the fourth greater than 24 over 180 times 0.0001. And then you take fourth root of both sides. And it's going to be 6.04. N must be 7, but in Simpson's rule, you have to choose an even number. N equals to be absolutely certain. But when you have a 6.04, we know that this is worst possible case. Actual error is almost always noticeably smaller than this. So that means n equals 6. Definitely 99% chance or more. N equals 6 should be okay. But to be absolutely certain, you have to choose 8. Alright? So these are, we didn't prove theorem 1 and 2. That is quite, takes a lot of work. And if you're interested in proof of those theorem 1 and 2, you have to take numerical analysis. Our university also offered that course. Okay? Numerical analysis. That take care of those proof of this error theorem, but many other approximation schemes, right? Not just the definite integral or solution of ordinary equation, partial differential equation, all right? Okay, so this is the end of part 2 of section 5.9, and 2 out of 2. So this is the end of section 5.9, okay?